even for commercial missions or missions that come across our plate that we could address in the near term, it's always looking at the comparison between solar electric propulsion and nuclear electric propulsion and wishing that we had the nuclear systems in place already. Because the breakthrough capability in terms of being able to move faster and move heavier payloads is just astonishing.
Just because the facts are A, if the narrative is B and everyone believes the narrative, then B is what matters. But it's our job in our industry to speak up proudly, soberly, and to engage people in this dialogue. Those 2.5 billion people that are in energy poverty, they need us.
America cannot meet this threat alone.
If there is a single country,
of course, the world cannot meet it without America,
that is willing to
but we're going to need you, the next generation, to finish the
overhaul
job.
nuclear regulation,
We need scientists to design new
and
fuels.
focus on net public
We
benefit
need engineers to invent new technologies. We
over absurd levels of radiation
need
protection,
entrepreneurs to sell those technologies.
then we will march towards this.
We need workers to operate assembly lines that hum with high-tech, zero-carbon
We have
components.
unlimited prosperity for all humans.
We need diplomats and businessmen and women and Peace Corps volunteers to help developing nations skip past the dirty phase of development and transition to sustainable sources of energy. In other words, we need you.
Okay, welcome to another episode of the Fire to Fission podcast. My name is Mark Hinaman, and I'm joined today by Vanessa Clark and William Kowalski, the CEO and COO of Atomos Space. Vanessa, William, how are you guys doing?
Hey, doing well today. Thanks for the invitation.
Yeah, super excited to chat with you guys. It's going to be a fun conversation. To familiarize our audience with you guys, why don't you just give kind of a brief 30-second self-intro for each of you? And it should be pretty obvious to folks who Vanessa and who William is, but yeah.
So hi, everyone. I'm Vanessa Clark. I'm co-founder and CEO of Atomos Space. So my background before Atomos was working in the aerospace industry in propulsion, both for launch vehicle design and manufacturing, interplanetary mission design, specifically on the propulsion system, and then also looking at Earth orbiting spacecraft propulsion systems. So trying to move things around in space has been my background before starting Atomos.
Yeah, so William Kowalski, co-founder, COO. Prior to this, I worked in finance. So I run everything that is Atomos as the corporation. Way back when I was much younger, I used to have a passion for space and physics. I had a theoretical physics website back in high school and a little bit into college, but just went in a different direction professionally. And yeah, just running everything. That's the money. And then I also lead all of our government affairs, national security, business development.
Awesome. Well, I can't wait to dive into Atomos more. We've already met once, and I have heard a lot of great stuff about what you guys are doing, so excited to dive into that. Before we do, let's hear a little bit more about your background. Well, let's start with you, Vanessa. What brought you to Atomos?
Yeah, so I have a couple of programs that I think are very foundational in my decision to start a company to try to solve what we're solving. The first was really my second job out of college. So I was working as a space systems architect on an international mission study. So working with the European Russian consortium, trying to answer the question, what are the best propulsion technologies we should be investing in to accomplish some really futuristic sounding missions? So I was at the time working at the German Space Agency. So working with a whole different consortium of space agencies and companies. And the missions that we're trying to do were get humans from Earth to Mars as quickly as possible. So in less than a couple of months. So right now, NASA's baseline to get astronauts to Mars is 6 to 9 months. Other missions we're looking at were like sample return from the outer solar system. So flying something out to Jupiter, being able to land on one of its moons, collect a sample, and have enough propellant to return. And also do that in a meaningful time frame, meaning you don't want to have to fund a science program to oversee that type of mission for 50 years. We wanted to do it in less than a decade. So one thing that becomes very apparent when doing that type of study is that the technologies we have to move around in space today are very inadequate. So chemical propulsion or electric propulsion, where the primary source of electrical power is solar energy, particularly as you move into the outer solar system. So the technologies that we were pursuing were nuclear propulsion, just similar to the nuclear navy. It really revolutionized how we can move around underwater, how long we can sustain a crew underwater, and obviously go under the Arctic and things like that. Very similar changes in capability in deep space. And so I actually started analyzing missions for the program a few months before that program got kicked off, and was able to design initial configurations that used very realistic near-term technologies, and we could get astronauts from Earth to Mars in less than 30 days, could get to Jupiter in a year, and really entered that program very pumped up, like, oh yeah, this is going to change something. This is really incredible technology.
We're gonna do it. It's gonna be awesome.
And then, over the course of the program, once the partners got involved, it became very apparent that everyone was bringing their pet technology to the table. Certain agencies were like, oh, I want to use this program to get this thruster funded or this conversion system for a reactor funded. And none of it fit together. It was a very Frankenstein spacecraft that we ended up presenting, and I didn't have a lot of influence or power being so early in my career. And I'm like, the thing that we ended up presenting was definitely breakthrough beyond what is possible today with solar and chemical propulsion, but it was really underperforming compared to what we could potentially do. We just made some small tweaks. Instead of having a Frankenstein spacecraft, actually did global optimization. We could do these missions where we could get humans from Earth to Mars in a very short amount of time. And the only reason we didn't land on these solutions was there were so many people involved in the decision. And there was a lot of politicking and fiefdoms coming into why that program really didn't go anywhere. So that was kind of a realization that, hey, it's not always barriers created by physics or engineering or material science that prevent us from doing things like this. Often it is the organizations, the politics, and the funding. So that was really one program I worked on that was very much a catalyst in terms of...
What was the process to get into it?
What was the process to what, sorry?
How'd you get that job?
So my undergraduate degree was in physics, so specifically nuclear physics. Realized very quickly that I did not like being a physicist, so I ended up changing my career to be an aerospace engineer. So I happened to be one of the few aerospace engineers in Germany who had a nuclear background. And so when this program realized it was going to pursue nuclear technology, I'm pretty sure I was the only applicant in Germany at the time who had these two areas of expertise under their belt. But a very interesting landing in Germany from Australia. It's one of the countries where if you do have a STEM background and a job offer, the visa just automatically follows. We're very forward-leaning in terms of immigration, and so I benefited from that initially.
Nice. Okay, so you realized that wasn't going to work with that large group of people. Yes. So what'd you do?
After getting a little more experience under my belt, I started looking for a co-founder. Also started assessing the near-term commercial potential of the technology and the service that we wanted to provide, which was providing transportation in and through space. And so there's definitely a 5-year discovery period, learning more about the industry and then also learning how to start a company. And that's a point at which I was introduced to William as a co-founder.
Well, then you ended up in the US.
Yeah, I did end up in the US. I tried. That happened somewhere in the middle because obviously being in Germany and in Europe now a decade ago, it became apparent that the US was the place to be, not just to pursue the market of in-space transportation, obviously with NASA and what is now the US Space Force, but also in terms of venture funding. So in Europe at the time, definitely lagged behind the US in terms of venture capital opportunities.
Yeah, I think it's still the case today. It's a different risk appetite between, we'll say, European investors and American investors.
Okay. Interesting. So, William, what about you?
Yeah. So, immediately before, I've had a very varied career. I've been all over the place. My first degree was in mortuary science. I was a funeral director for about a decade. Then ended up coming out to Colorado and worked in finance. Colorado being a heavy aerospace state, so 2% of the adult working population here are aerospace engineers. We are the largest per capita for aerospace. I knew a lot of people in the industry, and Vanessa at the time was looking for a business partner. And we were introduced because I had the passion for space and physics, knew, I wouldn't say I'm an engineer, but definitely have an engineering mindset and knew a fair amount about the science and what we were trying to do. So yeah, we had coffee when we had dinner, kind of talked through it, and then we ended up meeting up for coffee, and then we started working on it part-time together back in the fall of 2017 before we took it full-time together in 2018. Some of the things I think have been very applicable in Atomos today that I enjoy doing is in aerospace, I think engineering to cost is usually can be a really big issue. A lot of times problems in deep tech are solved by throwing money at the problem, and it tends to make not viable solutions. So really having a lot of financial discipline and kind of modeling out, so where do we want to go? What are kind of the economics we want to achieve, and really pushing to get the price target that we want as well. I think it's an Amazon mantra was frugality breeds innovation. And we certainly adopt that mantra here. I mean, we've bought 2 thermal vacuum chambers on eBay. We just bought a giant 6 degree of freedom robotic arm on eBay. If you push hard enough, you can find some really interesting things and save quite a bit of money.
Yeah. Okay, so Vanessa was looking for a co-founder. You were in the space. I didn't realize that 2% of the adult population in Colorado was aerospace engineers. Kind of makes sense.
It's
CU being here, right?
Yeah, CU. I mean, CU is the #1 college for NASA funding in the country, and I would say it was more traditionally legacy aerospace. It's still not in the venture scene or startup scene known as a big startup space. That's really more LA, but we are seeing that more and more in Colorado. There have been a number of companies in the startup space scene that have moved out here just because there's a lot of talent and a lot of people want to live here.
Yeah. And by legacy, I mean, a lot of it's like Lockheed, but there's also some kind of up and coming other companies that are like Sierra Space that are doing some really cool stuff, right?
Yeah. And, other in legacy, so you had Lockheed, United Launch Alliance, Maxar, and then, of course, what was formerly Air Force Space Command, which is now U.S. Space Command, and then you have the Air Force Academy, and there's a lot of DoD space presence here in Colorado Springs as well.
Right. Okay, so you guys met each other. Very exciting. And you mentioned finding a co-founder and working on this problem. What was the problem that you're trying to solve? Tell us about it.
So we approached it with an initial goal of providing in-space transportation services, because after that initial program I spoke to about looking at interplanetary travel, I went back into launch vehicle design and realized that we're prevented from doing a lot of not just exploration missions, but commercial missions, given the transportation infrastructure we have for space. Essentially, with launch vehicles, the higher an orbit you want to place your spacecraft in, it becomes exponentially more expensive because the rocket's capacity decreases exponentially. And the reason for that is really the rocket equation. The further you want to go in space, you need more propellant, and then you need propellant to carry that propellant. So if you look at the capacity of a rocket to a really useful orbit that is relatively high, it is a mere fraction of what the capacity of that rocket is in low Earth orbit. And so it's been not just over the past decade or few years or through companies like ours, but also really since the 1970s, NASA realized very early on that the best architecture for getting stuff to space and then to a high orbit is to actually use 2 segments. So use a high thrust rocket, like a space shuttle, to get payload or crew members to a low orbit in Earth. But then once you're in space, using a more efficient secondary stage to get them to their final destination. And that secondary stage can stay in space. And so that second stage, NASA initially called a space tug. The industry term now is orbital transfer vehicle. And so using this 2-step architecture really to do transportation through space is optimal from a physics perspective. But then also from a logistics perspective, you can reuse the system. It's not like a rocket where you until 8 years ago, you threw it away after the first launch. Like, it is a fully reusable system, like a delivery van or a connecting flight. And so it makes sense for so many different reasons. And so founded the company to realize this orbital transfer vehicle architecture for primarily commercial and Earth orbiting missions, but with the underlying mission to realize the next generation of in-space propulsion technologies, including nuclear propulsion. So that was the problem that we're trying to solve. So the near-term commercial market need, what service really makes sense for today's commercial customers, and then how do we develop a product roadmap that realizes the technologies that we want to see fielded in the future?
Cool. I'll say it back to see if I heard you correctly. There's some fundamental physics that make it difficult to get heavy stuff far into space.
Yes.
And once you're into space, moving stuff around is also challenging. And so NASA had a tugboat program, or the industry term was tugboat, but now it's orbital transfer vehicle. Do you guys use the acronym OTV?
OTV,
Yes.
yeah.
OTV. And I characterized this when I was with you guys previously as like a taxi or Uber for space, but is that inaccurate, or is there a different way to characterize it?
No, I mean, I think that's an accurate way to assess it, because if you could think of the three modes of transportation for space, inclusive of OTVs, you have rockets, launch vehicles, which would be like a Ferrari. Then you have onboard propulsion. So the majority of satellites, certainly all big satellites, have onboard propulsion for their own station keeping, minor orbit maneuvers, sometimes for orbit raising. That would be your scooter around the city. And then what has always been missing is kind of the bridge between Ferrari and scooter, which is really where we're fitting in, maybe a Prius Uber that can do a lot of stuff very cost effectively within the city limits. We don't have the speed and the thrust of a Ferrari, but we're very effective of moving things around within that region.
Yeah, that's awesome. Okay, so I mean, you've identified this problem. You've mentioned nuclear a couple of times, right? I mean, we say on this podcast that we talk about energy dense fuels and how they can better human lives. And that's kind of our catchphrase. But you guys are a space company, not necessarily a nuclear company, right? Like, what is the nuclear element to this?
So getting a little bit into different modes of propulsion. So there's typically, say, two general ways to move through space, and it's all to do with Newton's second law. So you essentially throw propellant out one end of your spacecraft or a space vehicle, and the space vehicle moves the opposite direction. So the velocity of what comes out your rocket nozzle really affects the efficiency of you being able to move your spacecraft. So you want that exhaust velocity to be as high as possible. So if you use chemical propulsion, the speed at which it exits is really constrained by the chemical energy of your propellants. So the best or the most efficient system that we have really fielded today is like the Space Shuttle main stage engines, which use liquid oxygen, liquid hydrogen. Now, the problem with that is that, it's really capped at a certain efficiency. If you want to be more efficient than that, you have to use a different method to accelerate your exhaust. So looking at electric propulsion. So historically, this has been a Hall effect thruster, gridded iron thruster that essentially create a charged propellant and then accelerate it using electrostatic, electromagnetic means, which is very efficient. The issue is these thrusters need electricity put into them. And so if you have a large solar array, typically, like for a very efficient system, the power or energy that you collect on your solar array, 60% of that can come out as thrust power if you have a very efficient system. Not all systems are that efficient. But it also means, like, if you want more thrust, your spacecraft gets bigger and then bigger and bigger and bigger and bigger. And, there's a ceiling where it doesn't make sense to get any bigger because you're also adding a lot of mass. So solar electric propulsion, so that's also a system that we're fielding. It is really great up to a certain point. And then if you want more thrust and higher efficiency, you need a different power source. And that's really where nuclear comes into play. And so really the breaking point for solar is somewhere between 60 kilowatts and 100 kilowatts electric power. And a 60 kilowatt vehicle is huge. For context, I think the International Space Station is around 85 kilowatts. And think of how large the solar arrays from that are. Like, this is already a really big system. And it's not that much power.
Comparison for something on that people would be familiar with?
A football field.
Yeah, the ISS is about the size of a football field.
Yeah, and you think, the business model that we're doing, the challenge of that would be, well, how do you actually rendezvous with clients in orbit? You have a significant control dynamics problem because you're moving this very large, somewhat floppy system because of these large extended arrays. And the ISS does not rendezvous with things. Things rendezvous with it. And we certainly wouldn't want our customers to rendezvous with our massive, giant football field OTV. So there's a point where just solar doesn't work anymore.
And this is, for our commercial missions, obviously we feel this, but for deep space exploration, it becomes even more problematic because the further you move away from the sun into the outer solar system, the power that you get from the same solar panels decreases. And so I think it's like out at Jupiter, it's like 1/12 the power output. So your thrust getting out of your little propulsion system would decrease to just a mere fraction of what it is around Earth. And so just decreasing thrust means you move a lot more slowly. So you can still move with great efficiency. It's just going to take a very, very long time to get there. Like trying to cross America with a little scooter that William mentioned in his transportation analogy. You could do it, but it's going to take a very, very long time. And in a lot of cases, that time is so long it's prohibitive for any type of interesting mission.
I guess hence nuclear.
Hence nuclear.
You need a more dense energy source that's smaller and easier to rendezvous with. Yes. So before we dive into the details of that, I feel like we skipped a step. I mean, you said, moving stuff around. What would be some examples of like spacecraft that need to be moved around?
Yeah, so there are a few different missions today that are very interesting for both commercial operators of spacecraft, but then also operators such as NASA and the US Space Force. So the first is to bring spacecraft into their initial operational orbit. So not all spacecraft want to go to low Earth orbit or the same low Earth orbit. And so once they get to space, they use their own onboard propulsion system to get to their final destination, or they have to overtax the rocket to fly beyond its optimal point. So a rocket has optimal payload capacity. We can put the maximum amount of payload mass in it possible when it goes to low orbit. And that diminishes exponentially if it goes further. So today, how spacecraft get to their operational orbit is a combination of overuse of a launch vehicle or expensive onboard propulsion. It's typically expensive because it's a system that's really just used once to bring the spacecraft into orbit and then potentially used again to either deorbit it or enter a graveyard orbit once that asset's finished its operational lifetime. So that's actually the primary mission that we've been targeting, because this is something that all spacecraft have to do. And with the evolving propulsion and launch vehicle landscape, services like ours are becoming more and more important. Spacecraft costs are coming down, and all of the spacecraft are currently being launched to around the same orbit, and they want to diversify. So we're talking to customers who want to go to different orbits that historically they've been priced out of, but now they want low prices offered by ride sharing, by SpaceX, but they want to go to a different destination. So we're bridging that gap for them.
Yeah, and some other, market segments. So beyond what we would call initial insertion, there's more life cycle services. So as I mentioned before, most spacecraft and all large spacecraft have their own onboard propulsion systems for, small maneuvers, and a big part of that in industry jargon is called station keeping. So we like to think of space being very static and everything follows its orbit, but in space with no atmosphere, small perturbances can start to impact things over time. So the gravitational pull of the Earth, of the Moon, of the Sun, of other planets does over time affect a satellite's orbit. So it needs to use propellant to stay in a specific location. Because if you think of something that's doing satellite TV or satellite communications way out in geostationary Earth orbit, 36,000 kilometers away, it has to be in a very specific spot so that it maintains that constant field of view over Earth. And if it starts to move, it could either lose its effectiveness or become totally inoperable. Now, a large part of what determines the lifetime of those satellites is how much station-keeping propellant it has. Because once it runs out, then that's it. It will slowly start to drift out of its orbital slot and then become useless, or even worse, become junk within very valuable space real estate. So something else that we're looking at with customers, we're in a conversation with quite a few of them, is, well, could we, either fly around GEO and kind of reposition people to help save their propellant, or maybe they've run out of propellant, so we can kind of do a little whack-a-mole and put them back to where they need to be and go to the next one and push them back down. Or even for those who want a little bit more consistency in that, do we just mate onto them and stay attached for an extended period of time and kind of take over that station keeping activity for them?
Cool. Yeah, that was going to be one of my questions, is how much propellant is typically on board some of these spacecraft and satellites. That surely it's not infinite.
Yeah, it is not. So if you look at a geostationary satellite, I think it's about a third.
Third to a half.
A third,
chemical propulsion.
It's chemical propulsion. A third to a half of its mass.
Non-physics nerds, it just stays in the same spot above Earth continuously, right?
Yes. Yep.
Yeah.
That's a lot. You're talking about a school bus size spacecraft. A third to a half is quite a bit of propellant. But one of the other challenging things is, this is true with most stuff in space, you can't exactly just go up there and check it. You can't, check the gauge on the satellite. So you have to kind of predict, based on each firing, how much propellant you actually used, and track that over a 10, 15 year life cycle. And the margin of error typically will be 12 to 18 months worth of station keeping propellants that you could be off by. So they need to account for that, and they don't want to run out and not be able to get to what is considered a graveyard orbit slightly above the geostationary Earth orbit. So they will say, all right, we think we're coming to the end, not being sure how much propellant is left. But this is also a problem with space debris. And one of the eventual markets we would move into in mitigating debris, because we also have probability clouds of where debris is, because you can't exactly go up there and double check. So it starts to accumulate, and we just do analysis and statistical analysis on the likelihood of this thing that we think is in this area might possibly hit you. But if you have highly maneuverable vehicles on orbit that can start to rendezvous with these things, actually see them up close, capture them, and then deorbit them, it makes it a more sustainable environment as well.
Yeah. So you guys plan to rendezvous. When you say rendezvous, this is like actually latch on to other vehicles, other satellites, and physically move them throughout space.
Yes.
Sounds simple when you put it that way, right? But this is not a simple thing to accomplish.
Yeah, so this is really the first thing that we are going to demonstrate in our first mission. So we have 2 spacecraft that are launching in February of 2024. This will be primarily a rendezvous and docking demonstration, so showing that we can detect, safely navigate to, approach safely, and then dock to a client spacecraft, and then also release it after we serve a mission. So this is obviously like a big technical challenge, but it's also for us like our foundational technology, because ultimately the benefit of our service comes from having orbital transfer vehicles already pre-staged in space. So what we want to realize is an architecture where our clients can launch their spacecraft to any orbit, and we rendezvous with their spacecraft in their affordable, low-energy insertion orbit and take them to their final destination. So having assets on orbit makes sense, and obviously part of realizing it is being able to do space rendezvous.
Yeah. And I mean, when I toured you guys in person, seeing some of your equipment and stuff that you've already manufactured and prototypes and drawings, it's really impressive. As a mechanical engineer by training, I was blown away. I was like, wow, these guys are smart. this is really cool.
Yeah, you should come out and see the facility now. One thing that we are commissioning is our upgraded rendezvous test bed. So we have a 20-foot by 50-foot frictionless floor. So this is many layers of polished concrete ground down. So it's super level, super smooth. And on this floor, we essentially have 2 air-bearing robots that can carry many hundreds of pounds in mass that we can precisely guide over this floor in a friction-free manner so they can simulate the relative dynamics between us and a client spacecraft, at least in 2 degrees of freedom. And then we've also added a hemispherical bearing, so we do have some of the roll degree of freedom that we'd get between spacecraft. But this is how we're really validating contact kinematics. So how hard can we touch a client, and how hard will we touch a client, and what will be our uncertainty in where we make contact with them? Because just like self-driving cars, there's going to be a little bit of uncertainty between what our rendezvous sensors, proximity sensors, and cameras are telling us and what is reality. So that test bed is in the process of being commissioned. It's very, very fun to see.
I mean, thinking about what you get, like you guys are flying spaceships into Earth's orbit, going super fast. Like how fast do some of these machines move? And then like slowing them down to barely touch and contact and like latch on to customer satellites. I mean, can you give a sense of scale for like how just the acceleration, deceleration, how fast these things go, and then how sensitive you have to be?
So the relative velocities in low Earth orbit can be 14 kilometers per second is typical. We won't ever approach a client anywhere near that fast. Our contact speed is 1 centimeter per second. So very, very gentle.
Yeah, I think so. You are moving.
I was in miles an hour.
Yeah, it's quite fast, much faster than a bullet goes, much faster. But as Vanessa said, the relative velocities are really what we care about, and those can be slow. But one of the issues that you have to deal with, particularly if you're doing this in low Earth orbit, is you're coming around the Earth every 90 minutes. And it is a fairly sensitive operation to get close to a spacecraft and rendezvous with it. So how do you structure your communication architecture so that you are in constant communication with your spacecraft? Say we have ground station in Denver, and our spacecraft is looping around every 90 minutes. Well, we can't exactly wait 90 minutes to talk to it again because it's on the other side of the Earth. So you have to think of ways to solve that problem. For our mission 1, we actually use a relay where we bounce off of existing satellites. So basically our signal goes up to GEO and then bounces back to us so that we can be in constant communication without having to build ground stations all around the Earth and they're all talking to each other.
Yeah. That's incredible. That's just, I mean, I don't know. I'm really impressed. Like, it's not an easy problem to solve. Okay, so just that deceleration, you're going from 30,000 miles an hour to like a 100th of a mile an hour, right? A centimeter a second. That's like 15 million times shift in accelerator and velocity. So that takes a lot of energy to do that, right? Like in order to accelerate to those speeds, but then also importantly, like decelerate or get, I guess, to the same speed that other vehicles are going. Where's that energy coming from?
So for our first systems, how we do orbital changes is using solar electric propulsion. So electric propulsion still makes sense because it really allows us to do large maneuvers. The thing that we're compromising on is that it often takes a bit of time. And so for this example where we're talking about 2 spacecraft essentially going different directions around the Earth, to actually do that change, it would be very counterintuitive. We ourselves would go into a different higher orbit and essentially let the Earth and the orbit of the client spin below us before we drop back down. So you're talking about kind of relative dynamics. It's not intuitive at all. It's not like driving a car where if you turn the wheel, you turn left. I think one of the best movies that actually explained this was The First Man, where they're talking about the Apollo missions and and the astronauts learning how to rendezvous in space, flying with the joystick. Like, it is, have to do some really crazy things to change orbits.
Yeah. Because if you want to catch up to somebody, you actually have to slow down. So you go to a lower orbit, and then your relative orbital velocity is faster, and then you catch up to them, and then you go back up. So yeah, very counterintuitive, which is what makes rendezvous in space very complicated, because it's not as easy as you're over there, so I'm just going to drive in that direction. Orbital dynamics really doesn't work that way.
Yeah. Okay. So you guys were called before Atomos Space. It was what, Atomos Nuclear?
Yes. Yeah. So our formal company name is Atomos Nuclear and Space Corporation. So we wanted everyone with whom we're working and investors to very much be aligned on our technology roadmap, that ultimately we do believe that space nuclear should be utilized for in-space transportation missions. We do DBA as Atomos Space for a couple of reasons. One of the most entertaining ones is that when we're like a 5-person company, some insurance providers, just when we're sitting doing analysis on our laptops as a group of engineers, didn't want to insure us. Because they were like, what's this nuclear? So it's still very important to us to have nuclear roots, and that's where we're going. But for practical reasons, we have elected to downplay that.
Gotcha. But the vision is to utilize nuclear for the power system. Am I thinking about that correctly?
Yes. Yeah. Even for commercial missions or missions that come across our plate that we could address in the near term, it's always looking at the comparison between solar electric propulsion and nuclear electric propulsion and wishing that we had the nuclear systems in place already. Because the breakthrough capability in terms of being able to move faster and move heavier payloads is just astonishing. So still a few years out from there, though.
But what is the long-term vision? I mean, it's to, would you have a nuclear reactor on board, or are you going to try and recharge somewhere?
Long-term vision is to have a diverse constellation, and there are going to be some missions for which it makes sense to have essentially a nuclear locomotive. So have a nuclear power source powering our electric thrusters. Now, the things that we're working on right now are in 2 different vectors. One is, how do we optimize the designs for our current systems so that they scale into nuclear? And then the other is looking at the nuclear side of things, like how do we design a reactor that is safe to launch, safe to operate on orbit, but then also optimized for mass, lifetime, and cost. So these are the 2 things that we're working on simultaneously, but long term, we definitely see like the high performance, say, vehicles in our fleet would be equipped with nuclear power sources.
Yeah. Awesome. You mentioned be able to launch into space. Is this prohibited now? Can people launch nuclear reactors into space? What's that look like?
It's not prohibited. So the U.S. has launched a little over 30 nuclear payloads in the past. One of them has been a reactor, the SNAP 10A mission back in the 70s?
1965.
60s. All the others have been what are called RTGs, radioisotope thermal generators, so a hot piece of plutonium that is generating kind of the thermal power you need to generate energy off of.
So one of the most famous missions that has an RTG is the Curiosity rover. So that's where it derives its power from. So the big Mars rovers that NASA's launched in the past 15 years have all had nuclear power sources, and not everyone realizes that.
Yeah, and so previous policy was dictated by a document called National Security Council Presidential Directive 25, which was a 1-page document that was basically be as safe as possible, and the president will sign off. So
why can't we still operate that? That's like
Well, I think for those listening who've had a lot of experience working with the federal government, things that can be open to interpretation can become quite dangerous because it can get really drawn out. And that was one of the big issues with this document was, well, then it gets kicked up to an interagency review, and that process starts to get measured in decades and tens to hundreds of millions of dollars of analysis. And it was just it was not commercially feasible. So in 2019, there was an update directive, a presidential memorandum on the launch of space nuclear systems, which then folded into Space Policy Directive 6 in 2020, which was a lot more prescriptive. The other big thing it said was, so NSC PD25 didn't specifically say this is only for government missions, but it also didn't specifically say commercial people can do this as well. It just said, president's got to sign off on this. So what SPD 6 did, though, is it said if you are a commercial entity looking for this authorization, then effectively, if you fall within certain categories of activity, so if you're a tier 1 or 2, kind of lower levels of radiation, then the FAA, who licenses launches, so FAA, Office of Commercial Space Transportation, is who does launch licensing. They have the authority to kind of bring in the respective experts to analyze this and then sign off on your nuclear safe launch.
Awesome.
Now, one caveat that I'd like to add to that is, so that is an update to the policy. And so regulations or regulatory guidelines have not yet been published. So even though it's permitted, there's still open questions as to how exactly. Like, what analyses do we have to present to the authorizing body to actually get approval? And while there are some criteria in terms of exposure to the public and probability of death or injury, like there's nothing else. It is very, very high level. And so one initiative that we're investing in as a company is a regulatory pathfinder that complies to the policy and will actually be the catalyst to help create precedents for approval and obviously help craft the regulations. So that's going to be our first nuclear mission that is really a minimum viable reactor. It is incredibly safe. How we're launching it, though, is going to be very similar to how we intend to launch more capable systems in the future. So it will set precedents for materials, methods of analysis, and then also launch configuration. So even though it's going to be a small mission, it's going to really be a pathfinder in terms of establishing how to do this and how to do it cost effectively in the future.
That's exciting. Yeah. So is there any risk of, I don't know, like a nuclear bomb going off when you launch this stuff into space? Should the public be worried about that? Or is that just ridiculous?
There are really two different segments of a mission that could potentially be hazardous. So the first is during launch. So with a space reactor, they are typically designed so that they have not been operated prior to launch, and they cannot possibly go critical during launch, even if there is an incident such as a launch vehicle failure. And this is also how we're designing our system so that the fissile material couldn't possibly go into a critical configuration during launch, or impact of a launch vehicle up on the ground, or submersion of a launch vehicle into the ocean, which is actually the driving case in many scenarios based on the spectrum of reactor that you have. So reactors are really intrinsically safe to launch. Contrast this to what NASA does with the Mars Science Laboratory. They have to have a lot of shielding on those launches because their plutonium is always radioactive. So launch of a reactor, very, very safe, unless you've done it wrong and it could actually go critical during launch. Radioisotopes tend to be less safe, but it's also why they've really been power limited, because they just don't want to launch that much at once. And then also typically launch over the ocean. So if there is a radioisotope thermal generator that falls into the ocean, there really is going to be no environmental impact from that incident at all. So launch is the one thing that really is covered in these updated policies that came out of 2019 and 2020. There is a very clear set of criteria for how to do that safely. The second area that could potentially be hazardous isn't so much like an incident on orbit or collision with debris or anything like that, because space is so large. Even if you did have like a runaway thermal event or a core meltdown, like as long as you don't go within tens of kilometers of it, you're safe. For context, no one goes within tens of kilometers unless you're actively trying to rendezvous with it. Spacecraft are spaced thousands of kilometers apart spatially typically. So it's really not an issue. And obviously there's not a large population of people
so
in
much
space.
more hazardous than any radioactive source that we put into space. Like, it's a non-issue.
Yeah, it is the smallest blip in this giant ocean of radiation that is space.
Yes. Yeah. So actually, to that point, one reason why NASA really likes nuclear propulsion for the humans to Mars missions is that the additional benefit of nuclear propulsion, so reducing the transit time to get humans from Earth to Mars, reduces the radiation exposure to those astronauts, more so than them living next to a reactor for a few months. So it is safer, and they get a lower radiation dose with nuclear propulsion. And so that's typically how it's assessed for space missions. And then, the other thing that also is addressed in the policy is, if you do have a reactor that has been operated, has residual radioactivity, it could re-enter. But really what UN guidelines have historically set and what the new US policy sets is a floor below which you shouldn't bring a nuclear system, so that by the time it re-enters, it is essentially benign and safe. So there is a regime for which you really shouldn't operate a reactor. We've also had discussions with companies who want to have nuclear-powered aircraft. It's a terrible idea. Keep them above a certain altitude, and they're totally fine. So, it's the regime and the guidelines that we have, do keep everyone safe.
We talked about this, the nuclear-powered aircraft with Garrett Bruhag on one of our first episodes. And
I'll have to go listen to that. Oh, I love Garrett.
Yeah. Well, I love the history of when the Air Force actually did it. It's amazing. I mean, great test case for the high temperature gas reactor, but right tool for the job, not really the right tool for that job. So I agree with you. Are there a lot of competitors in this space? I mean, OTVs, we spent a lot of time kind of explaining it because it was new to me, and it makes a lot of sense, but it seems like there's a lot of demand, and there will be a growing demand, but I don't know. Are you guys the only ones doing this?
No. When we really got started in 2018, we're one of 3 companies. There are probably 20 to 30 companies, all startups, with the exception of one, that are pursuing orbital transfer vehicles. Because if there's a market need, people can raise, if you're good, you can raise capital to try to address that problem. And so it is a very real problem. It's a good timing for us to go to market. But we're fortunate that we got started early, that we were able to get the traction that we had, and we'll be one of the first to field these services.
Yeah, and then, for context, launch was mostly real legacy operators. United Launch Alliance, which is a combination of Lockheed and Boeing, kind of formed this group. Arianespace in Europe, and then SpaceX came along and really mopped the floor with a lot of people and really took over quite a bit of market share. But then launch vehicles, particularly the small launch vehicles, was the new hotness in startup investing for space. And I think at its peak, there was something like 120 funded launch companies.
Wow.
All funded to significantly varying levels. But, there were so many because people said, oh, this is clearly an opportunity, and a lot of money was going into it. And, not to that extreme, but we have seen OTVs, particularly on-orbit mobility and logistics, to kind of broaden it a little bit beyond just OTV, is starting to become that, where there's a lot more money, a lot more interest going into it. But as Vanessa said, when we started, we heard from quite a few investors on, well, who would ever want this? Why don't they just use a small launcher? Small launcher will do all this. There's no need for that. And certainly that has not proven out to be the case, that there is definitely a need for on-orbit mobility, and particularly things beyond just low Earth orbit.
Yeah. That's crazy. But what are some of the timelines for nuclear in space? Do you think it's faster or slower than the commercial industry? Well, and I'll preface this with, we've heard the crusty guys that farm, I don't know, space nukes or whatever, like they think it'll be easier to build reactors in space than it will be on Earth, which I find frustrating.
In terms of manufacturing ease, no, but in terms of licensing,
yes. I'd agree with that.
Yeah. So timelines, we're not going to know until someone does it. But ultimately, like the engineering effort to bring our first mission to orbit, like we could complete that within 2 years, our first nuclear mission. The question is, how long will it take regulators to assess our applications and give us the thumbs up?
Gotcha.
In terms of more advanced system development, where we want to go, that engineering effort does have some kind of critical milestones, so integrated ground tests. There's a little bit that we need to do in terms of characterizing material performance in high temperature environments and also under radiation, which are longer campaigns. So that's more of a 5-year engineering effort maximum. But then it's also the question, how long is it going to take to get approval for this? So, if I had to put my money on something, I would say our first mission is going to be launching middle of this decade. Our higher capability system, we'll see. I don't want to put a number out there.
I like that. Faster than a lot of some of the terrestrial guys, right? Like, so, I mean, TerraPower and NuScale, they're like 2028, 2030. Like, that's better than some of their timelines. So,
yeah.
So does that include your first launch, or you mentioned using like a solar array for electric propulsion initially? And do you guys have plans for first launch plan or to test your rendezvous?
Mission 1 goes up beginning of February. So we're coming up on it real fast.
Are we gonna have a launch party? Are we gonna host an event for you guys here in Denver?
Okay, absolutely. So those 2 spacecraft are halfway through integration right now. So they're very mature, very much on the way to being ready to launch. And then we do have a few subsequent solar missions. So providing in-space transportation services. We had a really great business just using solar power, but we're not going to really bring about the change we want to bring or the value to customers that we want to bring until we realize nuclear. We're pursuing both in parallel.
Gotcha. Cool. Well, Vanessa, William, this has been fantastic. We're coming up on our time. Why don't you guys leave us with kind of your positive vision of the future? Where is it going in 10 to 20 years? What's this industry and space look like we'll say in the 2030s?
By the 2030s. I think we'll have in-space manufacturing, a lot more, we'll say, semi-permanent operations on the moon. But all of this is not going to be possible without in-space mobility and logistics. The way I kind of attribute it is, the California gold rush and how the Transcontinental Railroad really reshaped America by making it easy to move from one coast to the other instead of horse and buggy. And we really see ourselves as being that kind of change agent for what can be done in space. Did I steal your thunder?
I think that was great. I don't know what else to add.
That was great. Well, that's a great spot to leave it. We'll have to have you guys back on maybe after you guys launch. That'd be really exciting. So thanks so much for the time, guys. Really appreciate it.
Yeah, thank you.
Thanks, Mark.